Hello and welcome to this webinar to launch the white paper on industrial thermal energy storage, which has been produced by the European Energy Research Alliance's joint programme for energy efficiency in industrial processes. Today, a quarter of Europe's total final energy consumption is consumed by industry, 80% of which is attributed to heating and cooling processes. It's now estimated that this consumption contributes to around 60% of all industrial greenhouse gas emissions. So, could thermal energy storage form part of the solution to this global problem for industry? My name's Kate Sims, and over the next hour or so we'll be exploring the findings of this white paper and talking to the experts behind it to discuss the implications of industrial thermal energy storage in more depth. I'm delighted to say I'm joined in the studio by Professor Tony Roskilly, who is the Chair of Energy Systems at Durham University and one of the authors of this paper. Tony, hello, thanks for joining us. And joining us online to add to our discussions is our panel of experts. We have Dr. Ziwei Ma, Assistant Professor in the Department of Engineering at Durham University. Hello, Ziwei.
Hello.
We also have Professor Herbert Zondag, Senior Scientist at TNO and Professor on Heat Storage Technology at the Eindhoven University of Technology. Hello.
Hi.
So Dr. Salvatore Vasta is a research engineer at the Institute for Advanced Technologies for Energy in Italy. Hello, Salvatore.
Hello, Kate.
And last but not least, Dr. Hannah Kaukau, who's the Senior Research Scientist at Sintef in Norway. Hannah, hello.
Hello.
Now, there's lots to get through in the next hour or so, but don't worry if you miss something or want to refresh your memory about what you hear today, because you'll be able to download the white paper after we finish, and we'd encourage you to share it and the recording of this webinar with your colleagues. Now, you also have a part to play today because we want to hear from you watching around the globe. We have over 200 people registered in around 20 countries, including from as far afield as Australia, Brazil and China. So welcome to all of you. We'd like to encourage you to put your questions to the panel and to Tony. You do this by simply typing your questions into the chat, and we'll get to as many as we possibly can during the webinar. Now, throughout the webinar, we'll also be running polls we'd like you to contribute to. You'll see a question appear on your screen. All you have to do is choose an answer and press vote. To that end, we're starting with a question that we'd like your thoughts on. That question is, how important do you think thermal energy storage is to industrial decarbonisation and sustainability? You can choose from not important, quite important, very important, or don't know. I can see it's appeared on my screen, so do please cast your votes. Not important, quite important, very important, and don't know. We can see votes are coming in, so we'll look at your answers in a while. But while you vote, let's hear from EERA, the European Energy Research Alliance. Now, this white paper has been developed as part of its joint programme on energy efficiency in industrial processes. So here is Yvonne van Delft, who's the Innovation Manager with TNO and Coordinator of the joint programme, to explain a little bit more about this vision.
Thank you, Kate, for this opportunity. First of all, I want to show or tell about the European Energy Research Alliance. Our mission is to catalyze European energy research for a climate-neutral society in 2050. It's the largest energy research community in Europe, and it's a membership-based non-profit organization. And together we have 250 universities and public research centers in 30 countries of the European Union. The joint program, Energy Efficiency in Industrial Process, is one of the 18 joint research programs. And the vision of our program is to be European leading R&D community in energy efficiency in industrial processes. And we want to create synergy advantages between the different European research organizations and the industry to support the energy transition. What kind of activities are we working on? We have a strong collaboration with the set plan and the working group on energy efficiency in industry. We want to increase the impact to the industry with white papers like the thermal energy storage white paper, have increased the communication around energy efficiency, and also increased the connection to another network, the Spire network. And last but not least, we want to create a research agenda indicating research priorities for medium to long term. And one of the ways is to do that with white papers, as the thermal energy storage white paper. As you can see in the white paper, we have seen that the traditional energy efficiency measures are focused on reducing energy and the costs. And we think that thermal energy storage technologies have a huge potential in improving the heat recovery and significantly reduce energy use. We show that in the white paper with business cases and examples. One of the business cases we have shown in the white paper is the short-term storage, where we use the surplus heat from batch processes to preheat new batches and therefore reduce energy input and increase the energy efficiency. And an interesting example of that is a packed bed thermal energy storage unit, which is applied to a steel recycling plant of ArcelorMittal in Spain. And that's part of the RESLAC project. What we also did is one of the policy actions is linked with energy efficiency. What we think is very important is that energy efficiency, storage and flexibility are embedded as an integral part of EU transition plans. And therefore, we have written this thermal energy storage white paper to make this also show this to policymakers within the EU, but also national, regional and local authorities. Thank you, Kate.
So that's the background picture of why the white paper has been produced and how it aligns with policy. Now let's go to our poll, because I can see your answers are in. I'm delighted to say that most of you think it's very important, thermal energy, to decarbonisation and sustainability. 70% of you think it's very important, 21% of you quite important, 1% think it's not important. So Tony, I think we've got some work to do, and 7% don't know. So we've got some work to do during this webinar, but is that music to your ears that people are kind of on board generally with the message of the importance of this?
Yeah, I'm really pleased that that it was such a positive response to very important, because that's what we believe and that's why we produced this white paper. I think that it may not be representative because we've got a captive audience. We've got people that have joined this webinar. They already have an interest in thermal energy storage. And I think it's really important for us to look at the wider context and the wider knowledge and interest in thermal energy storage. And I think that if we polled a wider stakeholder audience, may I suggest regulators, etc., I think it would be a different result.
Tony, thank you very much. So hopefully we've got some work to do. We'll be able to do that during the webinar. So to the white paper, let's hear again from Tony now about what exactly this report covers.
Thank you, Kate. At the United Nations Climate Change Conference, COP26 in Glasgow, it was agreed that we must limit global warming to 1.5 degrees C, and that a drastic reduction in greenhouse gas emissions was necessary to reach net zero by 2050. Reaching net zero is crucial in dealing with climate change, but The solutions need to be consistent with sustainable economic growth and also contribute towards energy security. In short, we need to be more efficient and effective in how and when we use energy in the future. Since industrial activity is responsible for approximately 25% of total energy consumption and contributes towards 20% of total greenhouse gas emissions, it is crucial to decarbonise industrial energy use. This is dominated by heating and cooling energy demands and is reliant on the use of fossil fuels, such as natural gas, oil and coal. Over the next decade, we need to rapidly switch to greater use of renewable electricity and increased electrification of industrial processes. We need to expand our exploitation of solar and geothermal energy and switch fuels to alternatives such as hydrogen and biofuels. Also, we need to exploit the full potential of thermal energy storage. Thermal energy storage is an enabling technology which can play a significant role in decarbonisation of industry, whilst also providing greater energy flexibility and security. Thermal energy storage utilises the properties of different materials to store and release energy, which can provide a wide range of benefits such as supporting the efficient use of renewable energy, enabling surplus heat recovery to reduce industrial energy use, and decoupling energy supply and demand to enable intelligent systems to be developed. Thermal energy storage will also help to store off-peak electricity to enable energy backup for many industrial process operations. In terms of the EU's decarbonisation objectives, we've calculated that full rollout of thermal energy storage across industry could replace almost 1,800 terawatt-hours of fossil fuel energy, and this would be equivalent to a reduction of over 500 million tonnes of CO2 per year. The European Energy Research Alliance, EERA, Joint Programme on Energy Efficiency in Industrial Processes, commissioned this white paper and brought together the authors from leading research organisations across Europe. Its purpose is to inform industry, policymakers and stakeholders about the exciting role that thermal energy storage can and should make. The paper briefly outlines the energy consumption involved in industry and the current energy sources used for heating and cooling, and describes the range of thermal energy storage applications. We explain the different types of thermal energy storage and how they can be integrated into industrial processes and renewable energy systems. Potential business cases are presented, and we highlight several successful examples of thermal energy storage implementations in the EU. The paper discusses the main challenges with current methods and technologies which must be overcome if greater use of thermal energy storage is to happen quickly. We identify research and development to improve materials and systems and non-technical barriers which currently exist. Importantly, the white paper goes on to recommend actions to foster greater use of thermal energy storage in the future. This will strengthen the role of thermal energy storage with specific recommendations made for policymakers, funding agencies, business and research institutes. We're grateful to EERA for their continued support in these crucial activities across the European research community, and we hope the white paper can spearhead a step change in decarbonising industry. Kate.
Tony, thank you very much. And thank you, because I can see you're starting to ask some questions in the chat. Tony, just on what you were just telling us, Eliane Pusquedo, thanks for watching, Eliane, asked, does the white paper provide a breakdown of waste heat recovery versus direct electrification to arrive at the 1800 TWh?
Yeah, so actually the white paper covers all aspects of thermal energy storage and its applications. So that's in terms of utilisation of renewable energy and also recovery of low-grade heat and utilisation.
Perfect. So we'll find out more about that. That's what the white paper is aiming to do. But before we dig into the detail of how we might get to that future, let's take a look now at how thermal energy storage could be used in principle. Here's Alexis Servout to talk to us through one application.
Når det veldig kaldt ute, alle trenger strøm I byen, og det blir ganske stort topp på nettet, masse press på nettet. Og hvis det fortsetter sånn, og det blir flere og flere folk, da må vi oppgradere nettet, det som koster milliarder. Så løsningen som vi har da, det å få en distribuert løsning for å lagre varme lokalt, slik at når alle trenger strøm for å forsyne seg med varme, vi bruker den varmen som ble lagret I forkant, slik at vi trenger ikke så mye strøm fra nettet på den tiden. Så det en god måte å tilby fleksibilitet. Og på den samme måte som vi gjør det, vi kan også lagre varme når det masse sol og ganske stor produksjon fra solpaneler på bygningen. Det som også fremtiden I mange bygninger. Og så I stedet for å selge den, vi bare kjører den gjennom en varmepumpe, lagre varme, ha I den varmeveksler, og så vi bruker det når det ikke lenger sol. Det også en annen måte å tenke, det når strømpris veldig høyt, det som skjer av og til uavhengig av vare, uavhengig av kalde temperaturer og sånn. Så da også kan vi spille med fleksibilitet. Lav pris, vi lagrer varme. Høy pris, vi bruker den varme som ble lagret. Så det en god måte å tenke I fremtiden.
So we saw there an example of one application of thermal energy storage, but new technology means there are many different options. Dr. Salvatore Vasta from the Institute for Advanced Technologies for Energy in Italy can explain more about these developments.
Thank you, Kate. Today we will talking about the recent trends and innovation in the TS field. There is a growing interest in the application of TS, and R&D is trying to solve some critical issues for the integration of TS in industrial process. And these issues as for example, the reduction of cost. The recent trends and innovation in TS for the exploration of renewable energy in the industrial sector are mainly related to the advanced storage materials and on new configurations. But there is also an interest on the scale-up process of established technologies in order to fit industrial applications. To this direction, also ICT is supporting the introduction of TS with advanced simulation tools and design software to improve and accelerate the design process and the integration into the industrial field. As we know, we can divide TS technologies in three main categories, and the ones that are of interest for the industrial application are the solid sensible heat storage, PCM-based TS, and thermochemical absorption-based TS. About solid sensible TS, this is a very simple and safe way to store heat, especially at high temperature, that is perfect for the industrial application. Within sensible solid TS, concrete storage and packed bed storage technologies have been gaining interest in the last year, and this is demonstrated by the realization of some pilot plants. The company Energy Nest, for example, realized a modular TS system based on high conductivity concrete that they call Heatcrete for the integration in the steam grid of a chemical plant in Norway. And the same material is going to be used in an Austrian brick manufacturing industry and in a Dutch combined cycle power plant. Also, a Carnot battery can use a solid sensible TS. For example, Siemens Gamesa used this class of TS to integrate it in their pilot plant in Hamburg. The idea is to convert the electricity into heat and store as sensible heat. PCM materials are also interesting for integration in the industrial process. The main feature of PCM material is that they can provide heat at constant temperature, and this makes very interesting for industrial applications, especially for the steam production. there is an increasing interest in high temperature PCM materials, especially that one that can melt at temperature higher than 100 degrees. And R&D is supporting this class of TS by improving the thermal conductivity and thus the rate of charging and discharging by adding conductive filler materials into PCM. And this is supposed to lead to compact and cheaper storage systems. Thermochemical energy storage is also very promising. It's a technology that can be easily integrated in industrial process, especially for high temperature applications, since the storage period is independent of heat losses. Also in this case, R&D is investigating the potentiality of composite sorption materials and the benefits of using, for example, a salt in porous host matrix are the increased energy storage density and the enhanced sorption stability over the cycle. The feasibility of such technology solution has been demonstrated by a Swedish company called Saltix. Saltix developed a nano-coated salt for use in TS system called Enerstor. This salt demonstrates a high number of charging and discharging cycles with a low-cost material. Electrification has become an important focus for research and application because mainly of the CO2 reduction targets and the increasing shares of solar and wind electricity in the electricity supply grid. However, powering industrial processes by electricity creates issues related to intermittent electricity supply and the grid capacity. And these challenges can be addressed through energy storage. Power to X to power is a system that is proposed as a promising solution. Power to X to power system converts the electricity in something else that then can be stored. And then this energy stored can be converted into electricity back when needed. Finally, TES can also contribute to the phase out of existing fossil fuel power plants, in particular to coal power as part of the CO2 reduction plans. And some studies demonstrate this. The ITEST studies demonstrated that the feasibility of TIS integration in existing power plants as part of the German transition to a coal-free energy supply. Also, DLR and the University of Aachen is working on something similar. They are realizing a pilot plant within the project Store to Power, and this power plant will combine an existing coal power plant with a high-temperature storage to deliver up to the 10% of the steam needed in a steam cycle of a coal power plant. Thank you.
Salvatore, thanks very much. Lots of exciting developments there. Can I ask, you mentioned sorption heat storage there. That sounds very promising. What will be its actual role in the industrial field?
Yeah, thank you for the question. Yes, sorption storage system is the perfect solution for the integration into an industrial process because it gives the possibility to exploit the solar heat coming from concentrating system, but also to store the electricity from the grid, the extra electricity, by converting it into heat and store as sorption potential. Another important feature of the sorption TS is the low cost of materials. We have to take in mind that in this moment, very cheap material is perfectly suitable for application at 200 degrees and can fit a lot of industrial processes.
Fantastic. We are getting some more questions in. Thank you very much, guys. If we don't get to them immediately, we are logging them all. But I just wanted to ask this one from Syed Bentuba of you, Salvatore. He asks, can thermal energy storage be one of the flexibility solutions to push the peak of energy demand and reduce the electricity price, do you think?
Yes, actually, as I showed in my presentation, there is the possibility to store the extra electricity in the grid in the shape of heat in some kind of thermal energy storage technologies that I just showed. And then it's possible to convert again back this heat into electricity when necessary. Of course, if the management system is set to reduce the overall cost of the electricity, it's possible to store the extra electricity when the cost from the grid is low, and then use it when the cost is higher.
Fantastic, Salvatore. Thank you very much for now. Keep your questions coming in. Hopefully that will have given you a sense of how the different technologies might be used in the future. But what's the potential and value to industry? Here's our panellist, Dr. Ziwe Ma, to explain.
Thank you, Kat. I will talk about the potentials and values of industrial thermal energy storage, including its benefits, business cases, the cost, and some successful examples. Using thermal energy storage in industries can have multiple benefits, including greenhouse gas emission reduction, energy system efficiency and sustainability improvement, energy system cost saving, and electrical grid security improvement. These benefits are achieved through renewable energy integration, surplus heat recovery, thermal and electric peak shaving, and thermal backup. We calculated the potentials for fossil fuel saving and greenhouse gas emission reductions through the integration of thermal energy storage in the industry, as shown in the figure here. The rollout of industrial thermal energy storage throughout the EU can lead to a potential of 1,793 terawatt-hour fossil fuel replacement, leading to a greenhouse gas emission reduction of 513 megaton CO2 equivalent per year. The potential benefits of thermal storage are clear. However, its application in industries is lagging behind. Here are some potential business cases. For high temperature process heating higher than 250 degrees, electric heating could be used with heat storage in porous solids to decarbonize the heating process and enable the usage of low-cost electricity. For medium temperature process heating lower than 250 degrees, we can use either industrial heat pump plus heat storage or solar thermal system and daily or weekly heat storage, aiming to decarbonize the heating process and reduce the energy cost. For cold storage lower than 6 degrees, the fast-changing material can be used for storage, which enables industries to use lower capacity chiller and also low-cost electricity. For industrial surplus or waste heat, short-term heat storage can be used for batch process, or long-term storage can be used for space heating during winter for the industrial site itself, or can be exported to a district heating network. This leads to energy cost saving and carbon emission reduction. For thermal backup, thermal energy storage can serve as a kind of an uninterruptible thermal supply in case other heating options fail. This requires fast response time and high reliability. Heat storage, like steam accumulator, can be used as backup heat supply, avoiding boilers that otherwise would have to be available in standby mode. For industrial electricity demand, in addition to batteries, thermal options can provide low-cost solutions to meet the future need for high power, high capacity, and long-duration storage. The methods including Carnot battery, which converts electricity to heat and or cold for storage. Then the thermal storage can be either used directly for heat and cooling or converted back to electricity. Another option is compressed air storage with heat storage, which is similar to Carnot battery. The capital cost of thermal storage vary widely depending on the storage size and material. Generally, the specific capital cost per kilowatt hour reduced with increasing storage size. There is still a considerable uncertainty about the cost of thermal storage systems. The sensible storage is the most established and cheapest storage method. Large-scale water storage can be less than 1.3 euro per kilowatt hour. Underground heat storage is possibly to be installed at a very large scale and the investment cost can be lower than €0.5 per kilowatt hour. Latent storage has not yet been widely used. The most cost-effective fast-standing materials are about €50 per kilowatt hour. Sorption and chemical reaction thermal storage have the potential of very high energy storage density and a minimum energy loss in a long storage period, while also being cost-effective. It is expected that its cost could be similar to the latent heat storage in the future. In the table here, we show you the forcing objectives of the cost and a lifetime of thermal storage technologies by International Renewable Energy Agency. In the future, the continuous research and development on thermal storage and the expansion of the market will lead to further reduction in the cost of thermal storage systems. Here we give you some industrial thermal storage examples. The first one here is a high temperature storage, packed bed storage using low-cost byproduct for a steel plant. The storage temperature is around 700 degrees. The heat can be used for other lower temperature heating processes, and the potential of a full-scale operation can lead to 71 kilogram CO2 reduction per ton produced steel. These two are solar and hot water storage. The left side one is for brewery factory in Germany. The right side one is for road construction sector. The storage are used to replace the original gas boilers for energy cost saving. The storage temperature can be higher than 100 degrees if pressurized hot water tank is used, just like the left side example. This one is a steam accumulator at a large scale poultry processing plant. It uses 175 cubic meter steam accumulator because this plant is located where the electricity price is strongly affected by the variable wind power. So by using a smart control system, the steam accumulator can be applied to store steam from a kind of an electric boiler during period at a low electricity cost, and to deliver steam to the plant when the demand is high. Therefore, the energy cost can be reduced. This storage system is installed for a large-scale chemical plant in Norway. The used storage material is specially designed concrete. The storage temperature can go up to 400 degrees. It has a capacity of 4 megawatt hour, 10 cycles per day. It is used to balance the steam grid in the plant. The heat is stored from a high pressure steam in the low demand period, and heat is released when the demand is high. Thus, the energy saving is achieved, and the CO2 reduction is about 8 tons per day. Okay, that's all. Thank you.
Ziwei, thanks very much. So you talked about battery storage there. Can you compare the more familiar benefits of using battery storage with that of thermal energy storage?
Thank you for the question. So I think first, thermal energy storage is cheaper than battery storage. Second, as we mentioned, 80% of industry energy is for heating and cooling. So thermal energy is more directly relevant to industry energy system. It has wide application scenarios. For example, a lot of industry use gas boiler to generate steam for heating. So in this case, we can use steam accumulator, just as shown in the example, to store the heat laterally for usage. So that's what the battery cannot do. So that's a good example to show you that the thermal energy storage has wider application ranges.
And you mentioned costs there. Do you think in general that industrial thermal energy is a cost-effective solution?
Yeah, as Salvatore mentioned, there are different types of storage methods. Sensible heat storage is cheap. It has been developed for many years and technology are there. So they are cost-effective. But for latent heat storage and sorption and thermal chemical storage, they are less adopted by the industry or the market. Their market share is low. Now they are little bit expensive, but in the near future, as we are developing technology and also the market share is getting higher and higher, it will be cost effective in the near future.
Zoe, thank you. We've got a question that's come in here from Shala Husanova, who asks, do you think that using thermal energy storage to increase the source temperature of the heat pump can be used as a flexibility to charge or discharge while the electricity price changes? And can it be used to improve the coefficient of performance of the heat pump, do you think?
Yes, that's very true. So we know that heat pump efficiency depends on the temperature difference between your heat source and the heat output. So if you got low-grade heat, like waste heat from industrial processes or solar heat, you can improve the energy source, your heat source temperature. You got a lower temperature difference between your heat source and heat output. So you have higher COP and your electricity cost will be lower. Another kind of a application scenario is like you use low-cost electricity to power your heat pump to generate the heat for your usage and store that for later usage when your demand is high or the electricity price is high. And that's another way to utilize heat pump and storage to reduce your energy cost.
Okay, Zoe, thank you very much for now. Now, over to you again for another poll. It'll appear on screen in just a moment. The question I'd like to ask is, what do you think is the biggest barrier to industrial thermal energy storage? You can choose from financial viability, lack of regulation and legislation, lack of knowledge and awareness, and it's too complex to integrate with existing systems. That question again, what do you think is the biggest barrier to industrial thermal energy storage? If you can vote right away so we can see the answers as soon as possible. I can see some answers are coming in. Do you think it's financial viability, a lack of legislation, a lack of knowledge and awareness, or the complexity of integrating thermal energy storage with existing systems? Please place your votes now. I can see that some answers are coming in, and we'll give you just a few more seconds before we close the poll. Once again then, what do you think is the biggest barrier to industrial thermal energy storage? Is it financial viability, lack of regulation and legislation, lack of knowledge and awareness, or that it's too complex to integrate with existing systems? So it looks like people are still voting, just waiting for the things to settle. I think we'll probably go with that. So the results at the moment are that most people think that it's a lack of knowledge and awareness, Tony, closely followed by it's too complex to integrate with existing systems. Obviously financial viability plays a part, but also everyone's saying a bit of everything. I think the most strong answer is lack of knowledge and awareness, but in fact, Tony, they're probably all right, aren't they? It's a bit of a trick question.
Yeah, actually all of those factors are very important. When we've actually done workshops and with industrial stakeholders, I think it's fair to say that primarily the financial aspects are kind of highest, and that could be capital cost, it could be lack of incentivization from government to encourage the take-up, it could be the cost of actually deploying and utilization of thermal energy storage. That plays a big part, but all of those underlying barriers filter directly into that. So a lack of knowledge of the current technology and the opportunities kind of feed into that kind of financial barrier.
And that's what hopefully this webinar is trying to change.
Yes.
So with that in mind, let's hear a little bit more about the barriers that we've been talking about generally there from Dr. Hannah Kauko and Alexis Savot from Sintef again. And remember, do put your questions in the chat if you have any questions for our panel. But now here's Hannah and Alexis.
Thanks, Kate. So our task was to look at challenges and barrier to thermal energy storage. That's the chapter we addressed in the white paper. But let's take one step back first. The traditional objective of the industry when it comes to energy efficiency measures has been to look at reducing energy use and reducing costs. So in that respect, thermal energy storage has got a bit less attention in that time. But in the recent years, there's been a big change. Reducing carbon footprint has been much more in focus, and it will be even more in the future, as well as increasing the use of renewable energy sources on site in the energy processes. And in that respect, integrating thermal energy storage is becoming more and more necessary and viable to address the resilience that is needed in this energy system when it comes to intermittent energy sources and fluctuating energy prices. There's a lot to gain there with thermal energy storage. Now, why aren't we there yet? I will start with the technical challenges. Each of these thermal energy storage technology has its own specific area of application. They have their own niche market somehow. There's no one technology that fits all. That's the way it is. And each installation so far has been rather tailor-made. That means it takes a lot of engineering to implement technology on the industry processes right now. So we lack a little bit of standardized integration schemes when it comes to industry. But they have this thing in common, all this technology for thermal energy storage. They have the same type of goals when it comes to technological development. They all want to have high charging and discharging rates. They all want to have high energy storage density that goes with compactness. They all want to have a long lifetime and no reduction in energy efficiency over the high number of charging and discharging cycles that they will have to prove during their lifetime. Also, the low cost of material is important, and low cost of components if we want to meet the market. So it's very important there. A non-listed point also here, because it's not exactly a technical challenge, is that we all want to have technologies in that respect that have a low environmental impact. And that's necessary also because we can do it with thermal energy storage and maybe not so much with other energy storage technologies. Now, if we want to look more into details at what type of technical challenges remain today, that will take too much time, right? So, but if you just look at this table, you see that we look at different types of thermal energy storage technology: sensible, that are liquid or solid; underground thermal energy storage; phase change material; sorption, thermochemical storage. And for each of these types of technologies, they have different levels of maturity. So the technology readiness level, the TRL, is not the same. You see that for sensible storage in liquid form, that could be the hot water tank you have at your place, completely available commercially, so very high TRL. Works very well for short term. You see heat losses for short term are very low. It's green, it's all good. But when it comes to long term, it's red. There's a lot more to do to make it work. But then maybe too much to do. So then we look at the other technology that are maybe better addressed or better naturally made for that type of challenging. That could be phase change materials or sorption, thermochemical storage. And these technologies are maybe better when it comes to long-term heat or cold storage. But then we have a few changes to address with these technologies to make them work and make them commercial. Heat transfer could be improved. For example, durability and stability, to have a long lifetime with good performance over 25 years, the complexity of integration, the high cost still today because it's not really upscaled industrially. So there's a lot to do there, a lot of challenges that we can address with research. Now, I will leave the word to my colleague Hanne, and she will tell you more about the non-technical barriers.
Thanks a lot, Alexis. So most of the technical barriers can probably be solved, but the non-technical barriers may be more challenging to tackle. There's no doubt that we need to replace the fossil energy sources with renewables as fast as possible, and this will create a whole new demand for flexibility in the energy system. But even with so high share of industrial energy demand being thermal, there is a lack of awareness of thermal storage as a means of providing flexibility at the interface with a renewables-based power grid. So the figure shown here shows a possible fossil-free process production with an electric boiler or a high-temperature heat pump as the steam generator powered by renewable electricity. The steam generator is then connected to whichever thermal storage technology fits best to your application, supplying steam or process heat at the desired rates independent of the power prices. Such a system will also give the industry players a possibility to actively participate in the forthcoming flexibility market. When discussing flexibility, it's common to just think about batteries, but thermal insurance has some huge benefits compared to batteries. First, there's of course lower costs, And it's safe for both the users, considering fire and explosivity, for instance, and it's also very safe for the environment. It is scalable and is suited for large-scale applications and its longer lifetime, and it's based on using materials that are common and abundant. Of course, there are challenges as well, primarily that it's more complex and with respect to integration and operation, as both temperature, pressure, and thermal power need to be considered at the same time. Now, this figure here shows the main identified non-technical barriers, grouped according to market barriers, operational, financial, and legislative barriers. Apart from the already mentioned lack of awareness of the potential, the size of the current market limits the reduction in prices. There's also a lack of standardized products and integration practices. When it comes to operational challenges, we need more research and demonstration projects in order to convince the industry that the technology actually works. We need also more competent engineers for the thermal storage systems, as well as databases for the thermal storage materials. On the financial side, there is a lack of incentives that are specifically directed at thermal storage. And what could help a lot is having business models where the ownership of the power to heat and thermal storage infrastructure is not at the industry needing the steam, but at a third party that owns an infrastructure and produces steam optimally depending on the power prices and just selling the heat to the industry. Finally, at the moment, energy costs are still mainly dependent on the amount of energy, not the peak power, but this is already changing. On the legislative part, there's a lack of procedures for certifying the reliability of the technology, as well as legislation on the usage of new thermal storage methods and systems. And we need legislation that supports local sharing of energy resources, which is currently lacking. So, until recently, variability in electrical power prices has been low, and this has been reducing the viability of investments in thermal storage. But this is now changing, and which is increasing the attractiveness of thermal storage as a safe and environmentally benign form for energy storage. Thank you for your attention.
Hannah, thank you very much for that. A couple of questions coming in from our viewers, if I can ask you. First one's quite a practical one. In the report there, you mentioned short and long-term durations in context of what do you mean by short-term? How long are we talking for short-term? How long are we talking for long-term?
So for short-term, we often refer to from a couple of hours to a couple of days, like the maximum weekend or a couple of days. Whereas long-term storage, we mean often seasonal storage.
Fantastic. So weeks or months sort of thing. Yeah. Federica Halle asks, what is, in your view, the range of storage capabilities that thermal energy storage should have as a minimum to become useful in the industrial sector?
The main capacities or size range? I think that's, or was that the question?
Yeah, storage capacities that should be a minimum for thermal energy storage.
I think that just depends on the industry side and the application. I don't think there is a lower limit as such, but yeah, maybe some megawatt hours.
Okay. There's a question here from Adriana Schiavellis. What's your view on the barriers regarding the integration of thermal energy systems storage in industrial processes? TES technology is becoming more viable, but the bottlenecks often end up coupling thermal energy storage with the industrial processor units. So what's your view on the barriers of the integration?
So it depends, of course, on the type of storage. I think the most mature is a steam accumulator, in which you use the same fluid that you need the steam to store your heat, which is also your fluid for a process. But when switching to other types of, for instance, latent heat or solid storage, such as the concrete storage on here, there's more parameters to control, and there's this heat exchange process between the steam and your storage material. So these are for sure some integration issues. You have to take care of both the temperature and the pressure. Not sure if I answered the question.
Well, if she hasn't, do come back with an alternative question. But for now, I'll move on. Do keep your questions coming in. We're nearing the end of the webinar, so we will try and mop up any questions at the end. So keep them coming in if you can. So what have we learned from this white paper analysis of industrial thermal energy storage? Professor Herbert Zondag can tell us about the actions that the white paper recommends.
Thank you, Kate. Then let's go to the proposed actions. So first of all, I want to mention the awareness and policy actions items over here. So first of all, what we should all be aware of is that the need for heat storage will be strongly enhanced in the near future because of electrification and efficiency improvements of industrial processes. So think of increasing efficiency in internal process by heat recovery and batch heat recovery, or think of electrification using renewable electricity that is fluctuating in availability. So we need to have storage to overcome that. And since industry is using mostly heat, that will be thermal energy storage. So heat storage should become a standard option for industry. And policy actions we need for that is different types of support. First of all, support to demonstration and scale up of promising thermal energy storage applications. Because what we need is to increase confidence of industry to invest in this technology. So we need successful demonstrations. And also we need dissemination of best practices, which should therefore also be supported. Furthermore, of course, what should be continued is the R&D support to realize further advances in thermal energy storage. And finally, in policy documents, we need energy storage flexibility and efficiency as an integral part of energy transition plans at the EU, national, regional and local levels. Next, we also have technical actions. So first of all, we should undertake techno-economic system studies of the benefits of thermal energy storage in various applications, such as, well, the aforementioned over here. Then we need to run these test demonstration projects and do monitoring of these and make the monitoring results available by open access. Also to learn more about the functioning of these systems, to be able to optimize them and to give industry confidence in the proper functioning of these systems. Because of that, we also need to share best practices of optimal integration of heat storage in the system and disseminate this knowledge actively to all the stakeholders. Furthermore, we need to develop accessible test material databases, and we need to continue our R&D projects on potential advancements in thermal energy storage. Finally, we need market development actions. So we need the market to get the market going, and therefore what needs to be done is we need promotion and developing of new business models to support the exploitation of this. Promote and develop dynamic price structures, because if we have fluctuating prices of, for instance, renewable electricity in combination with electrification, that would strongly enhance the potential of tests to smoothen such fluctuations. We need to develop clear conditions and long-term perspectives for investments in industrial thermal energy storage. And we need to develop standardized test systems and independent testing institutes and testing standards to support technical development.
Herbert, thank you very much. Before we go to questions that are coming in, can I just ask, of those actions, what would you say are the ones with the highest priority?
In my view, the issue is that we need this market to get going. So the most important thing, I think, right now is that demonstration projects are realized, and that monitoring of these demonstration projects is shared in order to gain confidence in the market regarding this technology. And in order to promote this, I think also there we need support, also financial support, for these demonstration projects to, say for the first movers, you could say, to get this topic going.
So you talk about incentives there, aren't you, to motivate people to do these demonstrations? Yeah. There's a few questions that have come in here from our viewers. Amelia Motoaska asks, what do you envisage in terms of standardization of thermal storage solutions? Like, could there be battery off-the-shelf solutions? Will there be custom-made thermal energy storage solutions?
To some extent, or custom-made.
Then let's go to the proposed actions.
Design options, so that we can easily scale.
So first of all, want to mention the...
Sorry.
Just continue, Herbert, if you wouldn't mind.
Okay, yeah. So first of all, it's related to standardization. To have certain standard components, also standard ways of combining these components into systems, and standard integration options. And I think some standardization we can relatively easily do, for instance, in integration in steam systems. I think in the end, what we see now is that in many cases, still a lot of engineering and dedicated design has to be realized for specific demonstrations, which increase the cost. If we can smoothen this process, then also costs will go down, which will stimulate this market.
Thank you, Herbert. Another question here from Eliane Puskedu asks, have you considered the limitations in connecting to the grid because of particularly local constraints in the district network? Has that been a factor in what you've been talking about and looking into?
This is definitely an issue, but it's also an issue why you may need storage. For instance, if you have fluctuating demand locally, then you can also overcome this by using storage. So this is a peak shaving issue. So storage can actually solve part of these issues.
Okay, a couple more questions. I'm going to ask this one to Salvatore, if I can, from Rachel. Does charging and discharging, should it be bounded to the same location? Is that something you can answer, Salvatore? That's from Amelia.
It depends on the technology that we are going to use. In principle, yes, the same system can be used for charging and discharging process. Let's imagine, for example, a TS system used to store extra electricity from the grid. It consists of a conversion system that converts electricity into heat, and then a storage system that stores the heat for the time we need. And then we have another system to reconvert back the electricity, the heat into electricity. This kind of system that is commonly called Carnot battery allow the storage of electricity in the shape of heat. And yes, the charging and discharging process occurs in the same place in different time, of course. But if I use a different technology, I can use thermal energy storage to transport heat in another place. There is a pilot system that was realized years ago where it was possible to charge a TS and then put it on a truck and then use the truck to move this thermal battery to another place to discharge it and use the heat for another process. This is another application. It is another technology. So every technology has other different applications.
And that's part of the problem, isn't it? That there isn't this standardization at the moment. Can I ask this question to you, Hannah, from Jory Ruta? I think I've got the name right. Will the need and requirements for thermal energy storage be the same level all year round? Or are we going to have a peak at different times of the year?
I mean, I guess that depends more on the industrial side and their demands. Many industrial plants process all year round with the same rate, whereas others maybe have a pause at some stage of year. So I think that depends more on the application than the thermal storage technology.
Okay, so not a straightforward answer, that one. I'm just going to ask this one from Mustafa, who asks, is it a good idea to store heat by consuming electricity? If not, what can we do for storage in higher temperatures? I don't know if that's one that you could take, Ziwei?
Yeah, for store heat using electricity, as someone mentioned, we got something called counter battery. It actually store electricity by the form of heat and cold and transfer that back to electricity. What's the second half of the question?
What can we do for storage in higher temperatures?
For high temperature, yeah, normally that's for solid particles, solid packed bed, like what we did for counter battery or for other, as my first industry example, which is for a steel plant storage at 700 degrees. That's use solid stones, solid materials. So for higher temperature, higher than 250 degrees, economically speaking, that's solid stones, which is cheap and technology is ready.
Okay, fantastic. Thank you for now, panel. Tony, if I can ask you, it's a bit of a big question. We've heard lots of evidence there. But standing here today, what do you think the future should be and is for thermal energy storage? What's the best case scenario?
I think that I think it has a very important part to play if we're going to reach net zero and also have energy security. I think that in the best case scenario, we have developed policy and regulatory frameworks that actually accelerate the demonstration of thermal energy storage, that will stimulate the market, that will actually involve scaling up, that will then reduce costs and it will drive innovation further. So hopefully this white paper will actually play a small part in accelerating that trajectory.
Let's hope so. Thank you very much. That's all we have time for today. A reminder that you are all very welcome to download the white paper. You'll be able to find a recording of this webinar on the EERA website. I know people have been asking for slides as well. Hopefully someone will have replied to the chat about that. But if you want to look at the recording and get the white paper, that's on EERA-set.eu and also on the Net Zero Research Network website, which is net-zero-research.uk. You'll be able to see those addresses on screen now, and you can use the rather clever QR code. If you just scan that, they'll stay up on screen for a while and you'll be able to go directly to the website. Do please feel free to share this and the white paper with colleagues. Finally, there is a survey at the end of this webinar that we'd encourage you to fill out to help us understand how to improve webinars like this in the future. A huge thank you to all of you for joining us today. Thank you to our panel, and thank you, of course, for Tony for joining me in the studio. For now, though, goodbye.